According to a chemist known as Van Arrhenius, an acid is a substance that, when dissolved in water, produces hydrogen ion as the only positively charged ion. That is according to Arrhenius, and it is called Arrhenius' definition of an acid. This is evidenced in reactions of acids and other substances. Now, what Arrhenius is trying to tell us is that when we have a dilute acid such as hydrochloric acid, it ionizes to give hydrogen ions and chloride ions. From these ions, we are able to tell there is a cation and an ion. The cation is the positively charged ion, which from this ionization we only have a hydrogen ion. Therefore, hydrochloric acid is an Arrhenius acid. We can also have dilute sulfuric 6 acid. It ionizes in water, that is, when dissolved in water, it ionizes to produce 2 hydrogen ions and 1 sulfate ion. Again, we have 2 ions produced from that given a dilute acid, that is, hydrogen and sulfate, of which hydrogen ion is the only positive ion, meaning sulfuric 6 acid is an Arrhenius acid. Now, let us look at some of the reaction that will try to evidence that indeed an acid is a substance which ionizes to give hydrogen ion as the only positively charged ion. And the first case, we want to have the reaction between sodium hydroxide plus hydrochloric acid, the so-called neutralization reaction. So that gives sodium chloride plus water. Now, the equation is self-balanced. Let's try to write the ionic equation, that is sodium ion plus hydroxyl ion plus the acid will give hydrogen ion and chloride ion, forming, again, in the product we have sodium ion plus chloride ion. Then water does not ionize, and that's why we have water just in liquid state. To cancel out spectator ions, we have sodium, sodium, chloride, chloride, and that gives hydrogen ion plus hydroxyl ion, forming water. Now, it is true that water is formed when hydrogen ions present in the aqueous solution of the acid react with the hydroxyl ion according to the equation as shown above. Now, we have said that the two substances, that is, the acid and the base, react to give salt and water. And from there, we can see both salt and water are neutral substances. And that's why the type of reaction is known as neutralization, as shown below. Now, this sodium ion gives sodium hydroxide gives hydroxyl ion, hydrochloric acid gives hydrogen ion. The two combine to give us water. And of course, chloride and sodium also gives the other neutral substance, which is sodium chloride. Now, we have looked at that first case of neutralization. Let us also consider when now magnesium carbonate is reacted with magnesium carbonate reacted with what we call an acid, hydrochloric acid. And that gives magnesium chloride, carbon 4 oxide, and water. Ionic equation finally will have two hydrogen ions plus a carbonate ion, and that gives carbon 4 oxide gas plus water. From this reaction, it is clear that when hydrogen ions present in aqueous solution of the acid, it gives carbon 4 oxide and water after reacting with the carbonate ion. And we have seen that in the reaction between magnesium carbonate and hydrochloric acid. So different acids ionize in solution. For example, an acid like ethanoic acid, which is an organic acid, also ionizes in solution to give hydrogen ion and ethanoate ion. So it releases hydrogen ion as the only positively charged ion. Therefore, it is also called an Arrhenius acid. Let's look at the second definition of an acid, and that is according to Bronsted-Lowry. The so-called Bronsted-Lowry definition. According to Bronsted-Lowry, an acid is a proton donor. E.g., in the reaction between water and hydrogen chloride gas, or simply and hydrochloric acid, we are able to form, we can use hydrogen chloride so that we don't show much to do with dilution. That gives hydroxonium ion and chloride ions. Now that is water. Oxygen bonded to 2 hydrogen. Then we have the lone pairs. Then the acid donates a proton. That now gives hydroxonium ion. So we'll have the existing ones, that is proton, another, then the hydrogen ion donated by hydrochloric acid is attached there, and then that is now the hydroxonium ion plus chloride ion. Now, this is the proton donor. and therefore called Bronsted Lowry acid. It donates proton to that water, and from there we are able to have formation of hydroxonium ion. Another example, we can have methylamine, also reacting with methylamine like CH3NH2, reacting with water, and that gives CH3NH3 with the charge plus hydroxyl ion. Now again, this one donates a proton, and therefore this is what we call Bronsted Lowry acid, simply proton donor. And you can see this now has more hydrogen ion. Finally, in the same Bronsted Lowry, you can have ammonia gas, reacting with water, and that forms ammonium ion plus hydroxyl ion, which is simply ammonia hydrogen, hydrogen, hydrogen. So that is ammonia bonded well. Then water donates a proton, and that forms ammonium ion. That is the existing hydrogen, another existing hydrogen, another existing hydrogen. Then there is a lone pair, so the new hydrogen is accepted there. Then this is charged plus hydroxyl ion. So that is how water again behaves like a Bronsted Lowry acid. So in that case again, water is reacting as an acid. So that is all about the two definitions of an acid.